I am sure your mother goes and buys fresh vegetables from your neighborhood supermarket so that she can cook a delicious and nutritious meal for you. But before cooking, what is the process that is followed in your home? Are the vegetables cut and then washed? Or are the vegetables washed and then cut? Does it make a difference? Of course it does. What is the difference and how significant is it? Meet me in the studio and we'll find out the answer to this and much more. Welcome to our episode on enthalpy change. Let me begin by giving you a scenario. If you added salt to a glass of water, you would notice it readily dissolves. But what if you added powdered chalk, that is calcium carbonate, to water? Chances are you would be stirring for a long time and still not be able to dissolve it. The reason for this can be found in lattice enthalpy, one of the topics we will discuss today. In today's episode, we will take a look at enthalpy of solution, enthalpy of phase change, enthalpy of ionization, lattice enthalpy and its calculation, and the segment that puts your exam preparation in perspective, exam decoded. From the salt in the kitchen to antacid to kidney stones to just making a simple cup of tea, take a look at chemistry beyond the textbook, on your desk. The common thread that joins all these is called enthalpy. So what is enthalpy? It is a thermodynamic quantity equivalent to the whole heat content of a system. Enthalpy is denoted by the symbol H and is equal to the internal energy E plus the product of pressure P and volume V. Now, every chemical reaction is associated with a change in this quantity called enthalpy change. This is denoted by delta H and is calculated by the equation delta H is equal to H final minus H initial, where H final is the enthalpy of products and H initial is the enthalpy of reactants. Let us now discuss enthalpy change of a reaction that will occur when a salt is dissolved in water, with the example of ammonium nitrate. When we dissolve ammonium nitrate in water, the heat energy change involved is known as enthalpy of solution, denoted by delta H solution. This is defined as the enthalpy change when 1 mole of a substance is dissolved in specified amount of solvent. Watch what happens here. As soon as ammonium nitrate is dissolved in water, the temperature of the solution decreases. Since enthalpy of a reaction depends on the condition under which a reaction is carried out, we specify enthalpy under some standard condition, that is 1 mole of compound, 1 bar pressure and a specified temperature, which is generally 298 Kelvin. Do note that standard conditions are denoted by adding the superscript naught to delta H. Now, the enthalpy of a solution can be positive or negative depending on whether heat is absorbed or released during the reaction. In the experiment we just saw, when ammonium nitrate was dissolved in water, the decrease in temperature indicated positive enthalpy of solution. However, if you had used sodium hydroxide in its place, then there would have been an increase in temperature and consequently enthalpy of solution would have been negative. Remember my reference to chalk powder and salt? Well, I have them right here in 2 dishes each. When I add sodium chloride or common salt to this conical flask containing 100 ml of water and swirl, it dissolves readily. Let's see. So you can see that sodium chloride dissolved completely in water. Now let me try to do the same experiment with calcium carbonate or powdered chalk. I add some chalk. You can see that no matter how hard I try, it does not dissolve. Wondering why that happened? Let me explain. Ionic solids dissolve in a solvent by breaking ions free from the crystal lattice of salt. This requires a certain amount of energy known as lattice enthalpy. If the lattice energy is very high, the salt does not dissolve. This indicates that ions will continue to be in the lattice. However, if the lattice energy is lower, the ions break away from the lattice and dissolve. These free ions get attached to solvent molecules, and the heat energy change involved during this process is called enthalpy of solvation. And if water is the solvent, it is called enthalpy of hydration. Enthalpy of a solution using water as a solvent can be expressed as a sum of standard lattice enthalpy and standard enthalpy of hydration. Remember the question about washing vegetables at the beginning of the show? I think we can now answer that question easily. It is always a good practice to wash vegetables and then cut them. This is because a lot of good nutrients that are present inside these vegetables have low lattice energy and are highly soluble in water. Now, if you were to cut the vegetables and then wash them, you would be washing away the soluble nutrients as well. Now, you don't want to do that, do you? Let's get back to lattice enthalpy. This will help us to rationalize why some ionic compounds are easily soluble and some are not. Lattice enthalpy is the enthalpy change when 1 mole of an ionic compound dissociates into ions in gaseous state, denoted by delta H naught lattice. You have already learned that enthalpy changes in a reaction are independent of the path and dependent only on the initial and final state. This is known as Hess's law. If we apply this law to all the enthalpies involved in the formation of a lattice of an ionic substance, the route from one step to another is called Born-Haber cycle. Let us now construct a Born-Haber cycle for our favorite compound for the day, sodium chloride. In the first step, sodium metal is converted into gaseous form by supplying 108.4 kilojoules per mole in form of sublimation energy. Half of chlorine molecule is dissociated into atomic chlorine by supplying 121 kilojoules per mole of energy in form of half the bond dissociation energy in the second step. In third step, when 495.6 kilojoules per mole energy is supplied in form of ionization energy, it forms sodium ion. Atomic chlorine releases 348.6 kilojoules per mole energy as electron affinity. Associated enthalpy change is called electron enthalpy gain, denoted by delta H. In the last step, sodium and chloride ions combine to form 1 mole of sodium chloride crystal. Thus, it can also be said that lattice enthalpy can be evaluated by adding enthalpy change involved in the individual steps. Here we get lattice enthalpy for sodium chloride as 788 kilojoules per mole. Why don't we solve a numerical problem based on this? And you must pay attention when I take you through the solution, because numericals from this topic are high on examiner's list. The question is, given that lattice enthalpy for sodium chloride is 788 kilojoules per mole and enthalpy of hydration is minus 784 kilojoules per mole, calculate the enthalpy of solution of sodium chloride. The answer to this is pretty simple. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it is dissolved in a specified amount of solvent. Further, we know that for an ionic compound, enthalpy of solution is equal to lattice enthalpy plus enthalpy of hydration. Substituting the values we have, enthalpy of solution is equal to plus 4 kilojoule per mole. Lattice enthalpy of ionic solids is directly proportional to the ionic charge and inversely proportional to the size of the constituting ions. Higher the charge or smaller the size, higher is lattice enthalpy. And higher the lattice enthalpy, more is the energy needed to make it soluble. This leads me to an interesting observation, which is that many fluoride salts tend to be insoluble in water. This happens because many fluoride salts have very high lattice enthalpy, and higher the lattice enthalpy, lower is the solubility. Thus, they are insoluble in water. Speaking of fluoride salts, which one do you think has a higher lattice enthalpy? Sodium fluoride or lithium fluoride? LiF does, and the reason for this is lattice enthalpy is inversely proportional to size of ions, because smaller the ion, more is the energy required for ionization. Since the size of a lithium ion is smaller when compared to sodium ion, lithium fluoride has higher lattice enthalpy. At this point, I would like to ask you a simple question. Name the scientists who developed the Born-Haber cycle. No hints for this one. It's simple enough. Think about the answer while I go for a break. But don't go anywhere, as I will be back with the answer and much more on the other side. Stay tuned. Hello and welcome back to our episode on enthalpy change. The question I had asked you before the break was, name the two scientists who developed the Born-Haber cycle. Did you rush to topperlearning.com to find the answer, or is it something you already knew? Either way, let me answer it. The answer is Max Born and Fritz Haber. Did you get that right? I had promised that this was a simple one. Before the break, we had discussed enthalpy of solution and lattice enthalpy. And now we shall move on to enthalpy of phase change. Phase change is a very simple concept. It is the change of a substance from one state to the other. And as you are aware, solids on absorbing heat change to liquid, which on absorbing more heat change to gas. Now, enthalpy of phase change is defined as the enthalpy change when 1 mole of a pure substance changes phase under standard conditions. What do you think happens when ice melts? When ice melts, heat energy is absorbed, and this is called the enthalpy of fusion. The reverse is called the enthalpy of solidification or freezing. Note that both have the same value but opposite signs. Delta H fusion is always positive, and delta H fusion is equal to minus delta H freezing. You must have seen camphor that is used during pujas disappears sometime after it is burned. Or you must have seen room fresheners and naphthalene balls disappear into thin air after a few days. What happens to them? There is a change of phase, and these solids change directly to vapor phase. This process is called sublimation, and like other phase changes, it requires energy called enthalpy of sublimation. Scientifically, enthalpy of sublimation is the enthalpy change when 1 mole of solid substance sublimes at constant temperature. Under standard pressure, it is denoted by delta H naught sublimation. If you ever wanted to find the enthalpy of sublimation of a substance, you could use the Hess's law to calculate it. It's time now to answer a query.
Can I apply Hess's law to find enthalpy of sublimation of a substance to find enthalpy of fusion and vaporization?
Of course, it is really simple. As you know, sublimation is the process in which a substance gets converted into gaseous phase directly from solid phase without passing through the liquid state. Using this formation as well as the summation method based on Hess's law on adding the enthalpy of fusion and enthalpy of vaporization, you will get the value of sublimation. Delta H sublimation is equal to delta H fusion plus delta H vaporization. Despite its small size, we cannot remove an electron from an atom easily. As a result, removal of the electron will require a substantial amount of energy. The enthalpy change that accompanies removal of an electron from a gaseous atom is known as ionization enthalpy, and it is denoted by delta H naught ionization under standard conditions. For example, standard enthalpy of ionization of sodium will require 495.6 kilojoules per mole of energy to remove electrons from 1 mole of sodium vapor. Now, you can easily calculate the various enthalpies, can't you? Well, brush up your problem-solving skills to face similar challenges in Exam Decoded right after this break. Welcome back to our episode on enthalpy change. Before we head for Exam Decoded, let's take a recap of the key learning points from today's session. In this episode, we have seen enthalpy of a solution, which is the enthalpy change when 1 mole of substance is dissolved in specified amount of solvent, and is the sum of lattice enthalpy and enthalpy of solvation. Enthalpy of phase change, which is the enthalpy change when 1 mole of pure substance changes phase under standard conditions. Enthalpy of ionization is defined as the energy required to remove an electron from a gaseous atom in its ground state under standard conditions. Born-Haber cycle helps in calculating lattice enthalpy of ionic solids, as its direct calculation is not feasible. It's time now to put your skills to test with Exam Decoded. Welcome to Exam Decoded. I know you must be eager to know what exam questions you can expect. Let's begin with the rapid fire question round. 5 questions, 5 seconds to answer each, and a rating that will tell you how good your preparation is. So get ready. Here is your first question. Enthalpy of solution is the enthalpy change when 1 mole of substance dissolves in infinite amount of solvent. True or false? And the answer is false. That was an easy beginning. Let's hope your answer was false too. Here is the next question. Which of the following enthalpy change represents the enthalpy of sublimation for substance A? Option A, solid to gas. Option B, solid to liquid. Option C, gas to liquid. Option D, liquid to gas. The answer is option A, from solid to gas. Remember the vanishing naphthalene balls? And the next one is, bond breaking is an exothermic reaction. True or false? And the answer is false again. If you think you have cracked it, Here is another one coming at you. When ice changes to water, the delta H of this reaction is enthalpy of A. Fusion, B. Vaporization, C. Condensation, D. Solidification. The answer is A. Fusion. And the final one for the day is Born-Haber cycle helps to calculate lattice enthalpy for ionic compounds. True or false? And the answer is true. After all those false answers, we had to give you a true one. Now it's time to compare scores. If you have got all questions right, congratulations, you are a high flyer. If your score is either 4 or 3, then you are an achiever. Anything below 3 means that you are a learner and you need to pull up your socks and pay attention. Make sure you practice with a lot of tests and revisions on our website www.topperlearning.com. The topic enthalpy change belongs to the unit thermodynamics, which carries a weightage of 6 marks, which is a sizable chunk, and so it is critical to your overall performance in your exams. Questions from this topic usually test adeptness in numerical ability and can be asked in the form of short answer type questions for 2 to 3 marks. Calculate the enthalpy of vaporization in joules when 4.2 grams of carbon monoxide vaporizes at its normal boiling point. Delta H vaporization for CO is equal to 6.04 kilojoules per mole. This question is for 2 marks. Let us look at the answer for this one. We have been given 4.2 grams of carbon monoxide. From its molecular weight, that is 28, we can easily calculate the number of its moles, which is equal to 0.15. Solving till here will get you 1 mark. Now, enthalpy of vaporization is given as 6.04 kilojoules per mole and we are having 0.15 mole. Therefore, required enthalpy can be obtained by multiplying 0.15 with 6.04, which gives us the correct answer. On converting it to joules, we'll get the final remaining mark. Remember, it is important to always convert the final answer to the units that have been specified in the question. And now it's time for the examination expert on our show to guide you through some do's and don'ts that will help you avoid careless mistakes. So pay attention.
In the topic enthalpy change while preparing for your exams, students, you should focus on enthalpy of reaction, factors on which enthalpy of reaction depends, different types of enthalpies of reactions, relationship between delta H and delta U. For elementary substances in standard state, standard enthalpy of formation should be taken as 0. In the case of heat of neutralization or enthalpy of neutralization, when the acid and base both are strong, it is always equal to 57.1 kilojoule per mole. Students, I am sure with these simple tips you can score better marks in your exams.
Well, that brings us to the end of the show. Remember, chemistry is not just in your textbooks, it is all around you. And the more practical examples you find, the better your understanding of chemistry will get. So keep thinking. See you next time.